Welcome, guys. In the following video, we are going to study derivatives of logarithmic functions. We are going to use the following limit that we have seen in one of our previous lectures to show that derivative of ln of x is equal to 1 over x. Let's start by writing down limit definition of ln of x. So this is limit as h is approaching to 0 of ln of x plus h minus ln of x over h. Using properties of logarithmic functions, this can be expressed as ln of x plus h over x divided by h. Now, further simplifying this and expressing this as 1 plus h over x, and applying the following substitution, expressing h over x as nu, we'll end up with the following expression. When h is approaching to 0, nu is also approaching to 0. Also expressing h in terms of nu and x, h is equal to nu x. So this is limit as h. Now, instead of h, we are going to use nu, as nu is approaching to 0 of ln of 1 plus nu. H is nu x. So this is 1 over nu. Now, 1 over x is invariant of nu, so we can factor it out of our limit. So we are going to end up with the following limit, where we can write this down as ln of 1 plus nu to the power of 1 over nu, using properties of logarithmic functions. Now we know that ln of x is a continuous function, meaning that we can bring limit inside of ln. So we'll end up with 1 over x, ln of limit as nu is approaching to 0 of 1 plus nu to the power of 1 over nu. Okay, now this limit is familiar to us. It is equal to e. So we have 1 over x multiplied by ln of e, which is 1. So we have shown that derivative of ln of x is equal to 1 over x. Now let's find derivative of general logarithmic function, derivative of d over dx of log base b of x. Using properties of logarithmic functions, this can be expressed as d over dx of ln of x over ln of b. Now, ln of b is constant, which is 1 over ln of b multiplied by derivative of ln of x, which is 1 over x. So derivative of log base bx is equal to 1 over x ln of b. All right, now let's find derivative of the following useful function that extends natural domain of logarithmic function. Let's start by considering the cases when x is greater than 0 and x is less than 0. So first case, when x is greater than 0, derivative of ln of absolute value of x is equal to d over dx of ln of x and is equal to 1 over x. In case when x is less than 0, we have d over dx of ln of minus x. Using chain rule here, first we take derivative of ln of minus x at minus x, which is equal to 1 over minus x. Then we take derivative of inside function, which is minus x. Derivative of that is minus 1. So this is 1 over x, showing that derivative of ln of absolute value of x is equal to 1 over x. Now, let's use the following useful trick to find derivative of this function y. Let's take log ln from both sides. We'll have ln of y equal to ln of the following huge fraction, which using properties of logarithmic functions, we can express as the following sum. So ln of x squared plus ln of cubic root of 7x minus 14 minus ln of 1 plus x squared to the power of 4. So we'll end up with ln of y equal to 2 ln of x plus 1 over 3 ln of 7x minus 14 minus 4 ln of 1 plus x squared. Okay, now using implicit differentiation and differentiating by dx from both sides, we'll have 1 over y dy over dx equal to 2 over x plus 1 over 3 multiplied by 7x minus 14. And derivative of 7x minus 14 by dx is equal to 7. So we'll have 7 in numerator minus 4 multiplied by 1 over 1 plus x squared, and derivative of 1 plus x squared is equal to 2x. So dy over dx is then equal to y multiplied. So let's just copy this down here. Is equal to y multiplied by this expression here, which then you can further simplify, but we are not going to do it right now. And instead, if we want to derive dy over dx in terms of x only, then we have to substitute the value of y in terms of x back. Okay. All right. Now we have seen the following derivative of x to the power of r, and we have said that we can set r to be any real number. Let's show that why this is true. So y is equal to x to the power of r. Let's take ln from both sides. Ln of y is equal to r ln of x. Now let's use implicit differentiation, and we'll have 1 over y. Taking derivative base dx from both sides, we'll have 1 over y dy over dx equal to r multiplied by 1 over x. So dy over dx is equal to r over x multiplied by y, and instead of y, we are going to use x to the power of r, which is then r multiplied by x to the power of r minus 1. Okay, by the way, guys, the property that we have seen here, the trick that we have applied here is very powerful tool. It's extremely useful, especially when we are working with products, since ln can turn products and fractions into sums and differences. So for instance, let's assume that in some general case, if we have function f, let's call this function as u. Let's assume that we have u, which is product of several functions. Let's call those as fi's. Let's assume that they are functions of different variables. We don't care much. Then taking ln from both sides, we'll turn the following product into the sum of logarithmic functions. So that product is going to turn into the following sum of ln of f of y's. This is a very useful property, guys. Make sure to remember it. And this concludes our lecture on derivatives of logarithmic functions. We are going to see them in the following practice sheet. Thank you for watching.